Hi, everybody. Welcome to Math with Ace. We're going to be focusing on statistics today. We're journeying into the conditions that are necessary in order to perform hypothesis testing. Whenever you are doing hypothesis testing, you can always run numbers, but whether or not you should is another thing. When you are testing for hypotheses, we're going to be dealing with one sample today. You need to make sure that your data are random in order to be able to generalize to the population. You need to be sure that your sample was small in relation to your population so that you don't have to wonder about whether you're sampling with or without replacement. And you also need to make sure that you have large enough counts, be it successes or failures, or your sample size, depending on whether you're dealing with means or proportions, in order to actually have a distribution that is normal so that you can use those probabilities with your test statistic. So let's focus on the conditions that we're checking. They're very similar to confidence intervals, except when we're dealing with successes and failures, the way that we check this is assuming that the null hypothesis is true, and that's very important. So let's run through the two things that are standard for both means and proportions. Random. Again, we need to make sure that it is stated that our sample was randomly selected. And the reason that we do this is to be able to generalize to the population. We're trying to create samples that are similar to the population and reduce bias. If you have volunteers, that's not randomly sampled, but you can randomly assign, if you're talking about experiments, you can randomly assign those volunteers to try and help with this generalization to the population. And remember, this is the whole point of inference. Now, if I was to go to my class and ask my class whether they liked my teaching or not, that doesn't help me because they've signed up for my class. I cannot generalize that to the greater population. It's biased. So this is really important that we are randomly selecting. We also need to check that independence. And the way that we're checking independence is that we're making sure that our sample is less than 10% of our overall population. So we can say little n is less than or equal to 10% big N, where little n is our sample size and big N is our population size. Now, a lot of times you're not going to be given the size of the population, so you need to determine whether it's a fair assumption or not. And the way that we typically check this is we'll multiply our population by our sample by 10. And compare that to the population. If we're given a population size, then we need to make sure that that number, the sample size times 10, is less than the population size. So 10 little n must be less than or equal to the population size. And if we don't know the population size, we need to consider whether that's true or not. So maybe there's context clues in your problem that you're dealing with a large school district or the country or a large city. But if you say, you're checking You sampled 100 people in a small town. Is there more than 1,000 people in your small town? It depends. So you need to really be thinking about whether it's a safe assumption. Sometimes my students, when you walk into statistics class, your common sense hat typically goes out the window. And I don't mean that negatively. What I mean is, once we get into the realm of statistics, we don't typically associate it with what we know to be true. It's not a trick question. It's not something where, these are things that you would in general know, like whether the city is large or not. But when it comes to statistics, we forget that and we start to think about, well, in regards to statistics, maybe not. No. We're talking about in the real world. In the real world, are there a lot of people that go to our college? Okay. In the real world, are there a lot of people that go to this little tiny cafe on the side of the street? Like it's not disconnected from what we experience in the real world. So I want y'all to remember that it's not a separate topic. It's your day-to-day life. In your day-to-day life, what do you think? And y'all don't give yourself enough credit for your common sense. You have this information. You just need to let it out. Okay. Now, here's where the difference occurs in what we're dealing with as to whether we're talking about proportions or means. So again, remember, we're talking about one sample. There are hypothesis tests for more than one sample, but right now we're focusing on one sample. And is the parameter mean? Is it proportion? I'm going to start with proportions. And we are dealing with the large counts / normal condition. Now remember, we call it large counts because we'll be moving into chi-squared and different things where we are looking at expected counts, not just the normal condition, because chi-squared doesn't follow a normal distribution, but we have the same sort of idea that we're checking. And for a t distribution versus a z distribution, we want to make sure we can use that distribution. So is the parameter, I'm just going to go ahead and clean this up, is this a proportion? Or is it for means? Remember, when you're reading a problem, you should be reading for the word mean or proportion in order to help guide you. Or proportions are categorical. It's typically a yes, no, right? You have binary things that you're dealing with. Parameter, when you're dealing with means, you're dealing with a numerical data set and you have numbers given to you, or you're given the mean and the standard deviation, or you're talking about averages. So you're looking for those context clues to tell you what parameter you are focusing on. For proportions, since we are dealing with a categorical data set, you are looking for successes and failures to be at least 10. And remember, you have to check both. And now we are not talking about actual successes and failures from the sample. We are talking about expected successes and failures, considering we are assuming something about the null hypothesis. So that is the caveat for hypothesis testing. So recall, we are assuming the null to be true. Which means we have this null hypothesis where P is assumed to be some value. This is the hypothesized value. and the parameter is proportion or p. So p sub 0 is from the problem, and it changes every time. So that's why I'm not writing a specific number here, but it could be 20% of the population, 45% of the population, 85% of the population. It changes depending on the problem that you're dealing with. So we are looking at expected successes and failures. And what does that mean? That means that we need to multiply our sample size times our hypothesized value to see how many successes we expect. And then times that complement to see how many failures we expect. And both of those need to be at least 10. So the way that you check this is you say n times p sub 0 must be at least 10, and n times 1 minus p sub 0 must also be at least 10. What is that? Sample size times the hypothesized proportion and sample size times 1 minus the hypothesized proportion. So let me give you an example. Let's say I'm claiming that 25% of the population want it to rain today. And I sampled, 75 of my students. Well, that's not really random, but let's see how we would check this. What we would do is we would take n times p0, where this is p0 here. And we would take n times 1 minus p0. So 75 times 0.25 and 75 times 1 minus 0.25. And then I would determine whether those values are at least 10. What is 75% of, or what is 25% of 75? It's 18.75. And then what is 75% of 75? And that is 56.25. And both of those are at least 10. Okay. Now, I don't need to round these because, we can't have 18.75 of a person, but we just are looking for the fact that they're going to be at least 10. And so these are both at least 10, we're good to go. So again, it's very important when you are checking your conditions that you use the hypothesized value of the null to verify for your sampling distribution that it's going to be approximately normal. Going back to means, remember there's 3 ways that you can check that your mean is, or your distribution is going to be approximately normal. One is that the population is stated to be normal. And this is really like only in happy statistics land that this is going to be true. Because how do we know that the distribution is normal of the population? And if that's true, then we probably know the standard deviation, and then we probably know what the mean is, because you need the mean to know the standard deviation. So it's like, doesn't live in inference, but who am I? The second thing would be that the mean, or the sample size by the central limit theorem, if the sample size is at least 30. Now, in my class, we've practiced this. We've looked at sampling distributions. We've looked at that sweet spot of 30. And what I do want to say is that students very often, or people very often, confuse 30 and 10 with their large counts and normal. Successes and failures are proportion, that is 10. Mean is sample size, central limit theorem is 30, that's mean. So you need to be able to differentiate between the two. Do not get them confused. And then third, if your sample size is not at least 30, you need to graph it. And you need to verify by either a normal probability plot or your histogram and your box plot that there's no strong skewness or outliers. Now, if these conditions aren't met, you really should not proceed. And, we're in this like class environment where sometimes we're assuming the perfect situation, where we're assuming it to be normal, or we're assuming that it's random, and oftentimes it's not. So if you're going to go out into the real world and be a statistician or work in, data science field, these conditions are really important. The way that you set up your experimental design of before you're running your hypothesis tests are really important in order to be ethical and appropriate with your generalizations. So next up, what we're going to do is we're going to look at calculating test statistics for these two different hypotheses.